To begin our discussion, I'd like to pose a problem and walk through how we can possibly solve this problem together. Let's imagine we have a client. I'll go ahead and draw that right here. So this is our client device. And that could be a Windows computer, a Linux computer, it could be a laptop, desktop, it could be Mac OS, it could be a mobile device, any device that's actually going to make a request over the network. So here's our client device right here, and it's connected to, and I'll draw a little cloud here just to represent some type of a network. And then I'm also going to go ahead and put a server over here on the right. So here's our server. And let's imagine for this discussion that this server is actually running some HTTP web services. So it's running HTTP. Let's also imagine it's running FTP services. Now, FTP is an acronym for File Transfer Protocol. Think of an FTP like a file server. So if the client connects to the server asking for FTP services, the client can actually download or upload files back and forth between the client and the server. So those are two examples of application layer services, and that's why I put them in green right here. And we're going to leverage our discussions from our previous skill regarding the TCP/IP protocol stack. In fact, let me go ahead and put HTTP and FTP side by side right here. So those are the application layer services. Now, both of those application layer services at layer 4 use the protocol called TCP, Transmission Control Protocol. So I'll put that right here. They both use TCP. So the question I have for you, if the client is sitting here and it's making a request over to the server, how does the server know whether the client is looking for web services via HTTP, that application layer service, or if the client's looking for FTP services? Because they both run on TCP, they're both application layer services. How does the server know which service the client actually wants? Another scenario that also could pose a potential conflict or problem is if we have a client. I'll try another client right here. So this would be client number 1. Here's client 2. And we'll also draw a little cloud to represent some set of networking. And then for this scenario, let's go ahead and put server 3 and server 4. And up here, I'll go ahead and call this server 1. And this can be our network A or cloud A. This can be cloud B. So here in scenario B, let's imagine that this client has gone to this web server in one tab of their browser, and then from another tab, they opened up another website to this server. So in this case, both servers are running web services with either HTTP or the secure flavor HTTPS, which also both use TCP. But how does the client computer keep those sessions straight? I mean, one tab goes to server 3, another tab goes to server 4 within the browser, but how does the computer make sure the responses that come back from this server effectively go to the right tab or the right session, and that the responses from this server also go back to the right tab or the right session? How is all that tracked? And the answer to both of these scenarios is that we are going to use the concept of ports, meaning port numbers. So when we think of port or port numbers, we can think of them like identifiers. And when a server is running an application layer service, there is a well-known port. Think of it again like a number that's associated with those application layer services. And the well-known port for HTTP is TCP port 80. And the well-known port for FTP, File Transfer Protocol, is TCP port 21. And as we'll discover in another video coming up in this set, it also has some additional ports you can use as well, but we'll start off with port 21. So in scenario A here, when this client is making a web request, they open their browser and they go to a web server. Behind the scenes, it's not only going to the IP address of the web server so it can get to the server itself, but also it's specifying that the request is going to TCP port 80, which is the well-known port for HTTP. And that way the server knows, oh, this client is asking for an HTTP request on that port. And sometimes that's referred to as the server listening on that port. Or another scenario would be this client is making a request to the server, but it wants FTP services. That request coming in the server would be destined to TCP port 21. And the server is listening or paying attention to those ports, and when it sees incoming requests on those ports, it assumes, based on the well-known port for HTTP and FTP, it then assumes that, oh, the customer is trying to make an FTP request or an HTTP request based on the port number that the client has specified for the incoming request. So let me clean up scenario A here, and let's talk about scenario B. With scenario B, we have a client going to two different servers using the same application layer service, meaning the client is asking for web services, and in this example, we'll use HTTP, and it's asking for that from both servers. Now, each of these servers is going to have a different address, and that would be one way the client can keep track of them. But in addition to that, we also have port numbers associated with those sessions involved. So let's label these sessions 3, as in session number 3 for this first one going to server 3, and session number 4 for the session from the client going to server 4. For the first example here, for session number 3, when the client makes a request, that would be sent to the destination of server 3, including the IP address of server 3, so we get to the right server. And in addition to sending it to the server's IP address, that's the layer 3 component, at layer 4, it would also include the TCP protocol, because that's what HTTP uses. And it'd also be sent to the destination port number of 80, because that's the well-known port for HTTP services. But in addition to that, it's also going to include source information coming from the client. So it'd have the source IP address of the client here, that's client 2, but it would also include a source TCP port number. And let's say for this example, the source TCP port number that client 2 chose to use was 6783. And one might ask, well, how does the client know, what port number to use for a source port? And the answer is it just makes one up. It takes a look at all the logical port numbers it has in use for TCP, and it takes one that's a fairly high number, over 1024, and says, let's use this. It's available, and it just chooses it in the background and begins to use it. So the request from the client to server 3 would include TCP source port, in this example 6783, and the destination port would be port 80, the well-known port for the HTTP service. Now, if we compare and contrast that to the second session from client 2 over to server 4, let's put that right next to it. So for the session number 4, going from client 2 to server 4, the destination would include the IP address of server 4. That way that traffic could be delivered to server 4. But in addition to that, it would be destined to TCP port number 80. And that's because we're also looking for HTTP services. Now the client machine, the computer, does all that in the background. All we did was put in a URL and it simply went for it. However, for session 4 here, the source will be the IP address of the client machine, meaning client 2's IP address, whatever it happens to be, and the source TCP port will be some high-numbered port that the client pulls out of the air. So 6783 is already in use by client 2 as a source port. So let's say, for example, it chooses port 6784, a different source port. And that way, when server 3 is responding back to the client, it's going to respond back to that initial source port of 6783. And when server 4 responds back to client 2, it's going to respond back to the initial source port of TCP port 6784. And that concept is true for the layer 4 transport protocols of TCP, which is connection-oriented and does acknowledgments and make sure all the data gets back and forth, as well as for application layer services that use UDP. They both are going to include port numbers for source and destination, and that's how the clients and servers can keep track of the sessions involved and also know exactly which resource the client is asking for based on the well-known port for those services. Let's clean this up a little bit and chat about some of the additional application layer services that are commonly used in the world of IP networks, which is what we use on the internet today. And we'll also talk about the well-known ports associated with those application layer services. So here's a beautiful list of several application layer services, as well as the well-known ports associated with those services. So just as a reminder of how this logic works, let me just remind us that all these right here represent application layer services. So I'm going to go ahead and put them in green with a little arrow there, just to remind us that those are all application layer services. And then over here as the well-known port or ports associated with those services. Now, unfortunately, in this little output, it doesn't show, is it TCP or UDP? But that's okay. And also just be aware that some protocols, for example, DNS, there's multiple different flavors of DNS that we can use. And so the original flavor of DNS at layer 4 uses the layer 4 protocol of UDP. And the well-known port for a DNS server is 53. For example, let's imagine this server right there inside this company is a DNS server. So it's been configured with software, and if clients make a request, a DNS request saying, hey, what is the IP address for this name or that name, this server is ready to go. That server, the DNS server, would be looking for incoming requests that are using UDP at layer 4 and a destination port of 53. So when the server sees a request come in where it's UDP and the destination port is port number 53, it's at that moment it realizes, oh, this is a DNS request, and then if it's so configured to handle that, it can go ahead and respond to that DNS request. FTP is an application layer service that allows file transfer functionality. That's why it's the file transfer protocol, and it uses TCP at layer 4, and its well-known ports are 20 and 21. So 21 is the initial setup and the connection from a client to a FTP server, and then once they connect and authenticate and all that good stuff, then if they start to move files back and forth, the actual file transfer uses port 20. So 21 for the actual setup and control of the FTP session, and port 20 for the data. Now also, just be aware that there are multiple different flavors of FTP as well. So this is referring to the original flavor of FTP. So let me clean this up a little bit. And just as a reminder, in this column here where it says protocols, what it really means, because that's what it really is, these are application layer services. And then to color code this further, at layer 4, the transport layer, I'll just put L4 there. We are working with either the TCP in this column, the TCP or UDP protocol. So TCP is the one that is connection oriented, make sure the data gets there, and UDP is the layer 4 protocol that just throws the data out and hopes it gets there. It doesn't have any reliability checking. So TCP is considered to be connection oriented and UDP is considered to be connectionless. Or it could care less whether the packets actually get there. And that's just the way in my mind that I help remember the characteristics of UDP. And then the ports are associated with the TCP or UDP, whichever one's being used, the actual port numbers associated with that application layer service. So let's do this. Let's get on the list and I'll give you a quick overview of what some of these services do and the most common traditional layer 4 protocol for these application layer services. So FTP uses TCP. Port 21 for the actual FTP session, port 24 data transfer. Secure FTP as well as SSH both use TCP and they both use port 22 as the well-known port for those services. So if a client connects to an FTP server, for example, right here, and the layer 4 protocol is TCP and the destination port is 22, if that server is configured to support SFTP or SSH, that's how it knows based on that destination port that that's what the client is requesting. And then once the connection happens, they can further negotiate and then pull off whatever the client was after, whether it's a file transfer with SFTP or whether it's a command line interface, a remote shell, if you will, to the command line on that server. Now, Secure Shell is a great way to get a command line interface at a remote server that supports SSH. However, a less secure option is to use Telnet. Now, Telnet will also get you a command line interface access. Think of it like a command prompt to a server is insecure because it doesn't encrypt any of the traffic going back and forth. While on the other hand, SSH does encrypt the traffic going back and forth, which makes the actual flow of traffic more secure in the event somebody steals those packets off the network and wants to see what's happening. So let me clean that up a little bit and we'll continue our discussion. Simple Mail Transfer Protocol SMTP uses TCP and the well-known port for an SMTP server is TCP port 25. And one question might be, well, where exactly will we see this port information? And that's going to be tucked in and part of the little header as part of a TCP or UDP segment of data. So if we had a protocol analyzer, which we'll be looking at shortly, and we open up a protocol capture and looked at the details inside the TCP or UDP section of the protocol stack, it will include the port information. For the original flavor of DNS that uses UDP, and the destination port is 53. And as we discussed in a previous set of videos, DNS is for name resolution. So if this client says, hey, I need to know what the actual IP address is behind this server or that server, it can make a request via DNS to a name server and then get a response back with the IP address that it needs to go to. Another common protocol in the TCP/IP protocol stack is DHCP, and that runs on UDP ports 67 and 68. So 68 is the port that a DHCP client will use, and port 67 is the port that the DHCP server will use. And here's the purpose of DHCP. When a client boots up, if it's configured to get an IP address dynamically, meaning on the fly from a DHCP server, it can go through a DHCP process and get an IP address handed to it dynamically from a server. So let me give you an example of that process. Let's say we have a client here, and the client's been configured to get an IP address automatically, and we have a DHCP server that's reachable, and let's imagine it's on that same local network. Now for the DHCP process, there's 4 packets involved, and the first one's a discover. And that's the client sending a discover message trying to find a DHCP server. So the client will use a source UDP port of 68, and the destination port inside the UDP header would be 67. And that would be sent onto the network. And then the server would respond back with an offer. So for the offer, the server would source it from port 67. So the source port would be 67, and the destination port would be the port the client's using, which is 68. Again, all UDP. So the offer is sent from the server back to the client, indicating which IP address that client may use. And that's going to lead to the next exchange. And that's where the client says, you know what? I love the IP address you're offering. I'll go ahead and use it. And that piece is called a request. And that's coming from the client going back to the server. And in this case, the source port would be the client port of UDP 68 going to the server destination port of 67. And then the final piece, let me make a little more room here for us. would be the server acknowledging that the client is going to use that IP address. And that part is called the acknowledgement. And for that, the source port would be 67 coming from the DHCP server going to the destination port of 68. And again, that's coming from the server going back to the client. And that's all going to be UDP based. So the application layer service here would be DHCP. The well-known port would be UDP 67 for the server. And the initial source port for the client would be 68. So let's clean that up a little bit and let's continue on our list of application layer services and the well-known ports for those services. So for this protocol, Trivial File Transfer Protocol, unlike FTP, the file transfer protocol, the trivial version uses UDP, and the well-known port for a TFTP server is UDP port 69. Next, we have HTTP, which runs on TCP at layer 4, and the well-known port for a HTTP server is port 80. Another common protocol that's used all the time is NTP, Network Time Protocol. That's where a client is making a request from an NTP server asking for what time is it, effectively. And then they can synchronize between the client and the server so our clients can have the accurate time. So with NTP, the layer 4 protocol is UDP, and the well-known port is port number 123. ABC 123, tell me the time, tell it to me. So if that helps you remember the port number, that's great. And that's the actual well-known port for Network Time Protocol. Another common feature in networks is to manage the network from a central point or a few central points. And one of the protocols used to do that is an application layer service called SNMP, Simple Network Management Protocol. And with SNMP, it uses UDP and it uses ports 161 and 162. An example of using SNMP would be, let's say we have a management station right here that's probing and communicating with other networking devices. It can use SNMP, which behind the scenes is using UDP at layer 4, and the well-known ports of UDP 161 and 162 for SNMP. Now, another protocol that's often used in networks is a protocol called LDAP, Lightweight Directory Access Protocol. So I'm going to put a little note here, a little mark there rather, and also a little mark right here because there's a couple different flavors of it. They both use TCP, so TCP 389 for LDAP and TCP port 636 for the secure flavor of LDAP. Again, both using TCP. So what would LDAP or the secure flavor of LDAP bring to the table? Let's imagine that we have a server right here that has a listing of all of our user accounts and their properties, something like an Active Directory server. Well, instead of having to recreate all those user accounts and so forth, what we could do is enable LDAP services on the server where it would be then listening, if it's an LDAP server, on TCP port 389, or if we're using secured LDAP, it'd be listening on TCP port 636, and devices that wanted to check in and ask about, for example, authentication for this user or for that user, or to find out what members of a group a certain user is in, those LDAP requests going from network devices like firewalls and routers and other systems would be using a destination port of TCP 389 or TCP port 636, depending on which flavor of LDAP we had set up on that server. Another very common protocol is HTTPS, which is the secure flavor of HTTP. So think of it like web services, and the well-known port is TCP port 443. Now, behind the scenes, HTTPS, the secure flavor, is very likely going to be running something called TLS, like version 1.2 or TLS 1.3. And TLS simply stands for Transport Layer Security. And at the end of the day, it's providing web services via HTTPS. The traffic going back and forth is encrypted, and that's why it's called secure, or HTTP secure. But if we looked at it with a protocol analyzer, it'd very likely show up as TLS version 1.2 or 1.3. So let me clean that up just a little bit, and let's continue down our list. Next, let's imagine that this client right here wanted to go ahead and access a file server in a Microsoft networked environment. It's very likely the protocol that's going to be used to see the files on that file server and move them back and forth is SMB, Server Message Block. And SMB, that application layer service, uses TCP port 445 as the well-known port associated with SMB. Another common feature in networking with the TCP/IP protocol stack is the ability to send log messages to a centralized location. So if we want to take our log messages from these servers and this router and this firewall and the switch and send them all to a specific server, if that server was set up as a syslog server, which means it's listening on UDP port 514 and has all the software installed to make it a syslog server, that's the actual well-known port for syslog, UDP port 514. Now earlier we talked about SMTP up here, Simple Mail Transfer Protocol, and this is the insecure or unencrypted flavor of it. And down here we have SMTPS, and the S simply implies secure, where it's doing encryption. And for the SMTPS, instead of using TCP port 25 as up here, it has the well-known port of TCP port 587. So just as a reminder, as time marches on, many of these protocols have been improved and enhanced, and sometimes we may be using additional port numbers and different layer 4 protocols to support an updated application layer services. So the list here is for the more traditional flavor of these application layer services with their most common layer 4 protocol and the well-known ports for the original flavor of these protocols. Another common application in the world of IP networks is the concept of a SQL server. And that's how you say it, SQL server, structured query language server. Think of it like a database that has a lot of information that another device, a client, may need to request. And so if we have a SQL server running here, it's going to be listening or paying attention to TCP port 1433. And the well-known port for SQL Server is TCP port 1433. Another really cool application layer service in the world of IP networking is remote desktop protocol, where you can think of it like taking remote control of another computer so you can see and work with that device. And for RDP, if I have an RDP server, meaning a device that's willing to go ahead and allow an incoming connection from a client, we would expect that to be open and listening on TCP port 3389, which is the well-known port for RDP. And then because over the last decade or two, we've done a lot of integration with all kinds of network traffic, including setting up voice over IP telephones, one of the protocols associated with voice over IP is called SIP, the Session Initiation Protocol. And with SIP, depending on the flavor and implementation, it could use UDP or TCP, and it could be port 5060 or 5061, depending on the implementation of SIP. And 5060 would be for the unencrypted flavor, and 5061 would be for the encrypted flavor. So if there's a network where there's voice over IP and digital telephones that work over the IP network, it's very likely they're going to be using SIP, the Session Initiation Protocol, as part of that functionality. Now, if this seems like a lot of information, and it is, I would ask you to not fret. You don't really need to memorize every single possible application layer service and also memorize the well-known ports for that service. But as you continue to work with networking and as you continue to work with various protocols, as you see these over and over again, they're going to be easier and easier to recognize. And part of the reason why it's important to know what the protocols and ports are is because we may have firewalls or other devices we need to set up that may need to explicitly permit certain protocols and ports based on which application layer services that we're using in our network. So one of the cool things about the internet is that if you aren't sure, for example, okay, what is the protocol and port used by a service like SSH or HTTPS, the documentation is out there. So this is from the Internet Assigned Numbers Authority. I just did a search for well-known ports. And if we scroll down, it has a laundry list of the well-known ports for various services, and they're doing them numerically. And if we scroll down, for example, here we have port 20, and TCP port 20 be specific for file transfer for the FTP data, and TCP port 21 for the actual setting up of an FTP session. If we continue to scroll down, here's 22, TCP port 22 for SSH. If we scroll down further, here's Telnet with TCP port 23. Now here it also lists that UDP might be a possibility, but as far as the application of Telnet today, we're using TCP at layer 4 with the well-known server port of 23. And then as we scroll down, here's TCP port 25 for SMTP, and the list goes on. And I'll add this link, so if you want to use it yourself, you're welcome to. I'll add this link as part of the skill for your reference. And there's another point I'd love to share with you, and that is regarding the source port that a client might use when they're connecting to a service like an SSH server or an HTTP server, etc. Because when I was first learning networking about 30 years ago, I wasn't really clear on how the source port was chosen. So as a quick example of that, let's imagine that this client right here is going to this server right here, and let's imagine that server is running an HTTP service. So if this is our server right here, if it's running HTTP services, and I'll put that in green to match and remind us this is an application layer service, what that means also is that if that HTTP server is set up and running correctly at layer 4, it's also paying attention to incoming requests that would be going to the well-known port for HTTP. So for HTTP, which is right here, that well-known port is TCP port 80. And so this server would be effectively listening and waiting on that port for incoming requests. So when a client's making a request of that server for HTTP services, at layer 4, the destination port is going to be port 80. Now, as far as the source port is concerned, what is the source port going to be? So this is the destination port right here. What is the source port going to be? For most protocols, not all of them, but for most protocols, the client is going to take a look at what high numbered ports it currently has in use, and it's going to pick one that's currently available. So for example, if this client doesn't have the port 6783 currently in use, it can just identify that as what it wants to use for that session, and it will allocate that port and use that source port in the communication with the server. So if the server responds back to the client, the source port here in the response would be TCP port 80, and the destination port would be TCP port 6783 for the destination, for the response coming back from the server. And that's how they can track their sessions back and forth. And what we'll do together in this set of videos, we'll take 4 or 5 examples of this, including using a protocol analyzer so we can see exactly what's happening. Now, what I also want to point out before we leave this overview is that we have additional protocols that we can use, or application layer services can use at layer 4 besides just TCP and or UDP. And I'd like to discuss those with you for a moment. Other protocols besides TCP or UDP that may be used include ICMP. And one common use of ICMP is like a ping. A ping is a tool that we can use like from a client computer just to verify we have IP connectivity to a destination device. And that's using protocol ICMP, and it's not using TCP or UDP. It's a separate protocol together. In fact, these protocols also have numbers associated with them. So ICMP is protocol number 1. TCP is protocol number 6, and UDP is protocol number 17, and that's in decimal. So just to clarify, the TCP protocol number itself is 6, and then if we're using TCP, there's also going to be the actual port numbers as part of the layer 4 header here for the TCP protocol. And similar with UDP. UDP is protocol number 17, but when we use it, we're also going to have specific ports based on the services being used associated with that service. Sometimes in networking, we're a little creative. We send traffic over what's called a tunnel. Think of a tunnel like a logical path between 2 devices. So if we had a server out here on the internet and we had a client over here, we could logically set up a path using a tunnel. And the concept of a tunnel is we take the original traffic and then we encapsulate it again above and beyond the encapsulation we've already done, and then forward that traffic over this logical tunnel to the destination. Now, there's many different protocols we can use for tunneling traffic. One of those is a protocol called GRE, which is an acronym for Generic Routing Encapsulation, and that is protocol number 47. Another method that we have for tunneling is to use a security mechanism called IPsec. So IPsec is a family of protocols, and as part of that, there's a protocol called AH for authentication header, and that is protocol number 51. There's also another aspect regarding IPsec with something called ESP, and that's an acronym for Encapsulated Security Payload, and that is protocol number 50. So the actual memorization of these protocol numbers isn't the critical part, but I just want to make you aware of some additional protocols above and beyond just TCP and UDP that can be used as transport protocols. Also, as part of IPsec, there's something called IKE, the Internet Key Exchange, and Internet Key Exchange actually uses UDP, and the default well-known port for IKE is UDP port 500. So these are examples here of additional protocols we could use in the TCP/IP protocol stack here at layer 4. So before we leave this overview and we start diving into specific examples of protocols to help reinforce the concept of services, protocols, and ports, let's also talk about where traffic from a computer might be sent. And one of the most common traffic patterns between, for example, a client and a server is called unicast traffic. And unicast means one. So for example, from one device, like a client here, going to one server, like a server here. So that's traffic going from one source to one destination. However, sometimes we may need to send traffic to all the other devices on our local network. An example for when a broadcast will be needed is part of the DHCP process. When a client, for example, right here, is trying to discover, hey, is there a DHCP server on the network? So it sends out data on the network that's destined for every single other device and would be reachable by every single other device on that local network. And hopefully there'll be a DHCP server on that local network that hears that discover message and is able to respond with an offer. So a broadcast is from one device, like a client computer, trying to get its IP address via DHCP, going to all other devices on that same local network. And there's also a concept called multicast. So let's imagine that you and I want to send a message out to a group of individuals. So I'll go ahead and put person 1 here, and 2, and 3, and 4, and 5. And let's further imagine that we only want persons 1, 2, and 3 to get the message we're about to send. So I'm going to put a little check here saying they want it, they want it, they want it, and these other 2 people don't want it. Well, in the world of multicast, we can send out the message one time, and it can go to some of the people here, and the ones that aren't interested we can avoid sending it to those people. So with multicast, we're sending the traffic from a single source, and it's going to some or many. And an application of that would be, let's say we had a server that is pumping out a stream of content that's playing a TV show or a movie, and not every single computer on the network wants to go ahead and receive that. So by having a multicast server and then software at the clients that can specify they want to pay attention and receive that stream of data, we can have the server pump out the content one time, and then just the entities or the devices that want to receive it would be receiving that traffic, and the others wouldn't have to bother with it. And that's an example of multicast. And then one other option, which is really, really creative, is called Anycast. And regarding Anycast, let's imagine this is the Earth. And let's go ahead and put our user right here. So here's our user and their computer that they're connected to the internet with. And let's imagine they're trying to find a DNS server. So perhaps we have a DNS server here from Google, and the address is 8.8.8.8. And let's also imagine that further away we have another Google server also at 8.8.8.8. And over here we have yet another Google server at 8.8.8.8, all offering DNS services. So when the user makes its request for DNS, let's go back and take a look at the details here. That'd be going to the well-known port of 53 for UDP, looking for a DNS server. That's the address of the server. But in the case of Anycast, that traffic is going to be routed or forwarded to the closest DNS server, because all these DNS servers have the same exact IP address. And that's why it's called Anycast, where the client is one device and it's making a request to the closest server. And that's based on the routing tables, in this case, on the internet. So as far as how traffic can be forwarded or sent out, it can be any one of these based on the application that's being used. Unicast, one-to-one, broadcast, one-to-all on the local network, multicast, one-to-some or many on the network, and then Anycast is from one device to the closest resource, and that's going to be based on the routing on the internet, in the example of accessing a DNS server from Google. But the key is we have multiple devices, all with the same IP address, all of which could respond to that request, but the request is only forwarded to the closest one from the perspective of the routers between the user and the address 8888. So trust me, I get it. It's a lot of information, and check this out. What I want to do to reinforce some of the concepts that we've just discussed in this overview, I'd like to walk you through some specific examples with some common IP application layer services, just to confirm what is their layer 4 protocol they're using and what are the well-known ports involved with those application layer services. So we're going to continue this journey and start drilling into the details to reinforce those concepts in the next video, and I'll see you there in just a moment.